team, my friends. We have many questions from the pre-class talking. Hi, I do have the recordings actually up now, finally. Oh wait, let me give you these back. These are your last homeworks before I forget. Oh, you're welcome. No, it's not bad at all. None of them are bad.
I'm not sure what I mean by that either.
Okay, it's not me. It's not just me. Bless you again. You feel like you're getting sick? Is that why you're masked up?
No, a lot of people around me are
Everyone's
getting
been
sick,
getting
so
sick
I'm
lately.
just like,
I saw
Smart.
a group of freshmen just buy a shit ton of COVID tests, and I'm like, oh.
Oh no.
Bad. Which ones?
I don't know.
Bastards.
It wasn't okay.
Keep
It
them
wasn't
away
me
from
who
me.
saw it. It was my friend who saw them, and before I can turn around, the elevator door already closed. I'm like, shit. Ugh. But I figured since they went up the elevator, it's not on
No,
our floor.
that's not true. The kids take the elevator up to the second floor.
oh yeah.
And that
they
makes
do.
me irrationally upset.
I don't
Because you can't
understand
take one flight of stairs.
that.
So which one's
A
Yeah.
bunch of freshmen just bought a bunch of COVID tests.
Oh, everyone's really COVID.
Cool.
Yeah,
Great.
cool? Let's just close the school.
Yeah, yeah, actually.
I really hope not, because like if we do like another pandemic thing, then our graduation is gonna stop.
That is not gonna. If it happens, it'll be way before graduation. I think it would be this fall. What's that?
That might still affect the graduation, because I heard a bunch of shit with COVID, and I'm like, I don't remember it, but I'm like. Anyways,
Yeah, but they already did it once. They learned how to deal with it.
that is true.
Sure.
Yeah, Zoom.
If there's anything humans do, it's learn stuff. All right,
Sorry.
friends, homework. What do you want to talk about? Lots is what I hear.
0.16, maybe later, but before that,
She said, for sure, we're getting to 2.16, but not
Yeah.
like, wait a damn minute.
0.18, I'm pretty sure I'm not doing it wrong, I'm just spelling confused.
Well, you just have to plug something in because he doesn't want us to solve the delta epsilon, right?
Yeah. Wait. A 2.18.
2.17.
Oh, okay. Yeah, I just want you to use the Cauchy-Riemann equations there. Yeah. My God, don't go to the definition.
So
My God.
most of them, I got like either 0 equals 0, or like ux not equal to dy. So that means they aren't differentiable, right?
I kind of know. That was all like a little out of context, so I'm not quite sure. Like, so tell me your process.
Okay, so for example,
Yes.
f is like f of z equals imaginary part of z.
All right, let's get up here and do this, right? Because that wasn't an assigned one, was it? Or was
I
it?
think so, yeah.
Well, then let's do the other part. Let's do the real part, okay? So let's do f of z equals real part of z. Cool.
Okay. So that's gonna be f of z equals x.
Yeah.
So then that's gonna be like u equals x and b equals 0.
Yeah.
So u of x would be 1 and u of y would be 0.
Yep.
And b of x and b of y both would be 0.
Yeah.
So that means u of x is not equal to u of y, and u of y is equal to negative b of x.
Yeah, so that one checks out, right?
Yeah.
That one checks out. But this doesn't check out, and there's no variables in this,
Yeah.
so there's nothing we can do. Let me so right now, this isn't differentiable anywhere, it can't
Yeah.
be. Well, what if I modified it a little bit? What if I said, let's take the real part of x squared, or real part of z squared. So we really just get x squared.
Yeah.
And then we come down here, and this will be 2x, because, let me write this down.
Yeah.
Oh wait, sorry, u is x squared. u with respect to x is 2x. So now, these two, this still holds,
Yeah,
but now I need to have this for differentiability.
yeah,
And so that means only at x equals 0. So this one is actually differentiable when x is 0, in other words, along the entire imaginary axis. So this is the only restriction that I'm given on the Cauchy-Riemann equations.
so we can like mess with the equation to make something?
So say that a little differently.
Because we started with like real part of Z, but then when it wasn't working, we changed that.
No, I'm just changing it to a new problem. It's not,
Oh,
this isn't something I would recommend doing in the don't go and modify the problems.
yeah, that's what I'm
No, let's imagine this was the problem, so I'm trying to kind of get to, I think,
Yeah, no,
maybe.
okay, let's see, I did not have that anywhere. Oh, no, actually I did. There was x equals y.
Okay, so that would be all along this line in the plane. So if the Cauchy-Riemann equations are only satisfied when x equals y, then that means z has to be a number of this form,
Yeah.
and that is the only place I'm differentiable on that line.
Yeah, that's what I said, like differentiable at every point where x equals y.
Yeah, that's perfect.
But if I said it was analytic, but then like Noah also mentioned it isn't like an open, like not an open disk, but like a fuzzy line disk. So I guess it's not analytic.
This is not analytic anywhere. Yeah, because as you said, you need fuzziness around the point where you're also differentiable. So, yep,
Okay.
not analytic, but certainly differentiable on only that line.
What's that when it's x equals 0?
Restriction.
Okay, cool.
Okay, yeah, thank you for asking. Does that help a little, Labina, on?
Yes, it does.
Good.
So if it's 0 equals 0.
So 0 equals 0 is just a tautology. It's just no information is provided.
Okay.
Kind of like here, right? We got the 0 equals 0 on this equation.
Yeah.
It just doesn't give us anything helpful. O is true.
So we can't come to a conclusion whether it's differentiable or not, or can we just say it's not differentiable since the other one isn't equal?
That is correct, yeah. So like in the original example that we had
Yeah.
with this, then that is just not differentiable anywhere.
Okay. Okay.
All right, that sounds good. I like that. Yeah. What else do we want to talk about?
2.16.
2.16.
Yeah.
Okay.
Where is it? Okay.
So I've given you a lot of different examples of very simple functions that weren't differentiable.
Hold on, let me.
Wait, so just for me.
Okay, yeah.
Read 2.61 aloud so I can, 2.16 aloud so I can make sure that we have the same
Understood. Okay.
2.16.
Oh, yes.
Yes.
Can I just see your 216? Because mine is.
Prove that f of z is given by a polynomial.
That is not the problem. Right?
Right.
So the one. Okay.
Okay, I'll just.
Sorry, I need to like get the. Apparently not this version. What version? This is 153. What do you all use? 154. Oh well, that will do it. Yeah. So the problem I was looking at is prove or find a counterexample. If u and v are continuous, then f of z equals u plus iv is continuous. If u and v are differentiable, then f is differentiable.
Oh,
So it's really that second part that I'm kind of like interested in. Does that sound like a way better problem?
Seeing as none of us have tried this problem.
Which is awesome, yeah.
Great. Maybe let me take a gander at it. And then
Yeah, please take a gander. Here, you can just look at
Take a gander.
that. Can I see the problem that you thought I was assigning and maybe?
This
Oh, that's a cool problem.
I'm
Wait,
I'd
so
be interested
bad.
to know what it
Ow.
is, but I don't know.
so to the 216.
Well, you can. What I was doing is just like expanding it to heck. Like you can expand each into a bunch of terms, and then if it's like if I can prove this term, then all of the sum of these terms is this. and then all the sum of these terms must also be true.
Are you okay? Are you stuck? Are you struggling?
Yes.
Okay,
Shoveling?
struggling.
Struggling, okay, I was like,
Easily confused.
prove that if f of z is given by a polynomial, then z is entire, so that should be, well, let's take a look at how that might work.
So our 2.16 or your 2.16?
No, you're the old one that you don't actually have to do anymore, but let's look at it.
So we're just not doing.
Do not do this problem, please, do 217 instead.
We want 217, beautiful.
And in 217, there are two parts to it, so like, if the parts of the function u and v are continuous functions, is the original function continuous? And I'm gonna just tell you the answer is yes, and show why, or argue why. You don't have to get delta epsilon-y, but like, you know, give me a reasonable argument. And then the second part is what I really want you to do, and that's if u and v are real differentiable functions, then f is complex differentiable. And look through the very first example, I think I gave you a non-differentiable function. I gave a couple that were super simple. You just gotta get simple. There, stay simple, nothing complicated on 217. 216, a little different, let's see here. So f of z is a polynomial in z. They want us to prove that if that is the case, then f is entire. What can you say if f of z is given by a polynomial in, and I kind of think that maybe that second part is what will help us understand the first part, and now I see why Noah was foiling the hell out of things.
It's
Yeah.
like,
Yeah.
take one of the terms and then say that you foiled it, and then be like, I can split this foil into a real part and an imaginary part. And then if it's multiplied by a real and imaginary part. But then again, I didn't get to the part where I took the u of, like the derivative of both sides.
Yeah, the Cauchy-Riemann stuff.
Yeah, so that might not be a true argument.
I mean, I think we have some results here that could answer this. I'm just gonna take this clip off really quick. Whose book do I have? Oh, thanks, Luke. So I think there's a couple of results in here that are pretty helpful, and maybe not. This book doesn't have a lot of results in it, which is kind of a drag. Boy, they really want us to get in there. I thought we had like a basic class of functions that were differentiable. I'm not really seeing that. Let me think about this one and come back with an answer on, I don't want to waste time. I want to answer other questions. This I want to think about and see if there's like an elegant way to do it.
Like,
We'll do so.
just so I can-
Oh, okay, thanks, okay.
Thanks, Luke.
What other problems did you want to talk about there? Or did we already do that?
Just for 2.17, if it's saying if u and v are real differentiable, so does real mean like on the real plane?
Yeah, so the u, when we write this, when we write f of z is some real function plus some other real function, we're assuming that this just outputs real numbers,
Okay.
and this just outputs real numbers. So, you know, even so something like, I wouldn't get too crazy.
Yeah.
Like honestly, that's probably not differentiable anywhere.
Okay. So we have to show that if those are differentiable, then f of z should also be differentiable.
Yeah, yes, and I mean, let's just get ourselves a couple of basic facts that you can always use, is that polynomials, it's literally the result of that problem you thought you had. Polynomials are, in Z, are entire. That's just like, you're gonna be okay, you got a polynomial, just like in the real plane, real line, totally good. Rational functions, which is a ratio of two polynomials, are analytic on their domain. Right, so saying this is entire means it's analytic in the whole plane, so that's a very strong statement. Rational functions are analytic on their domain, so e.g., let me give you a quick example. We've got f of z is 3z plus 2 over z minus 1z plus 1. That function is differential everywhere except at 1 and negative 1, where the denominator goes to 0. So domain, i.e., where we don't divide by 0. So this function is analytic on complex plane minus just negative 1 and 1. Put little holes, pop little holes on them, and you're good to go. Does that help, Lavina, like kind of clarify what is holding you back there?
I think so. I'll have to like work through it and see.
Okay.
Can we just prove this with examples or counter examples, or do we need to actually do a proof? Because I know we did, I think, one kind of proof with the u, x, y, and the v, x, y.
So for the continuity, so there's like two things to address there, right? First is the continuity. Really what I would just like to see is do you understand what continuity means? And if you go to the basics, like continuity means if I change the inputs a little, the output changes a little.
Yeah.
Right? There's no big jumps. So we've got a function, looks like that. This is continuous. This is continuous. Is this whole thing continuous? So like, it seems pretty reasonable that it is, and maybe just give me like a heuristic argument on how that might roll.
Okay.
You don't get delta epsilon, you don't need to. You could.
I won't.
Okay, you could. It's not too bad. It's actually not that bad, but I don't want that. And then on the other one, I want a counterexample, because that is not true.
Okay. Yeah, because like even if they are differentiable, f of z can be not differentiable.
Like this.
Yeah.
Like this is beautiful, right? But this is not differentiable anywhere. Because why? Well, here's u, here's v. Don't use this. All you gotta do is not use this example, which should be pretty easy. So ux is 2, vy is 3, and those aren't equal.
Yeah.
So, yeah.
Okay.
What else?
That's it for me.
That's it? Okay. Are you good? That was you're mostly
Yeah.
concerned about that one that is
Yeah.
no longer an issue. Cool. All right, here, let's do a little just impromptu karma-free practice of derivatives. Let's just do a little fun. This is just like light. This is like a party favor for our math party. A party favor.
Yeah, that was a question I had, like, just derivatives work the same way?
Derivatives work exactly the same way.
Okay, what if I have something written in terms of u and v?
Then, let's actually, let's see, do I have an example here of talking? Let's talk about that. So let's go through this example that I've got right here, because I was going to give you this question. So, where is, and let me know if this is what you're thinking about, Noah, this function so something like this, where is this differentiable and what is its derivative at that place? Is that the kind of question you're, like how do you take the derivative of this?
Yeah.
Okay.
Well, I guess you could just take the derivative with respect to x or y.
Well, so it comes, we gotta go back to that proof of the Cauchy-Riemann equations.
But I'll just try this first, and because I haven't actually done this. And then I'll give.
Well, so remember where the Cauchy-Riemann equations came from. we took the derivative of a function in two different ways. And one of them ended up with this, and the other one ended up with this. And these have to be the same. So this was like when we approached on the x-axis, and then when we approached on the y-axis, we got something like that. So yeah, and I think this is right. Because these two, we took the derivative in two different directions and they have to be the same. So the Cauchy-Riemann proof says, oh, okay, well if these are the same, then that has to be, shit, now I got it, there we go. And then this is here. So this first one says that ux, the real parts have to be equal, that's how we got this. And then the imaginary parts have to be equal. So in other words, u with respect to y has to be the opposite of u with respect to x. But Noah, this is our formula. I can use either one of these formulas and get the same answer.
Okay.
On the area of differentiability. And so that's going to be a little bit subtle. And we'll see that here. But let me just give you this to you and ask, let's just practice right now. Where is this differentiable? And if you want, go ahead and figure out what the derivative is. Is it analytic? Or is this differentiable? Analytic? And what's its derivative? Where it is differentiable. I haven't been running to the restroom like I used to, so.
Are you not hydrated, Dr. T?
I'm not, I don't think I'm as hydrated as I used to be back in the
I'm
day.
gonna need you to get on that.
I mean, you're right.
Drink water, damn it.
I mean, get rid of some, come back, drink some.
Beautiful.
All right.
Oh, wait, no.
Hell yeah. I love that for you. Sounds absolutely fucking miserable. Biology. No offense. Biology sucks.
It's fun.
I didn't go chemistry before I went bio. Or like physics. Any science but biology.
I would go physics before bio.
Now, physics would be like, I am literally held at gunpoint.
Physics was
I think that's a little traumatic.
Yeah,
Just a little bit.
No.
And I'll, this Friday I'll be in my office from like 10:30 to noon. Definitely gonna be in there.
Same.
What's that?
Same.
Same, sweet, that'll work out.
So together.
Might even talk.
You think you're gonna be in your office and I'm not gonna bother you? Are you joking me? Do you know who I am, Dr. T?
Well, sometimes you're working on other stuff.
It's usually statistics.
Are you gonna be a math club today?
Are we gonna have cake?
No, there's no cake.
Are we gonna have food?
There's gonna be food
There's always
and drink. There's gonna be Capri Sun and whatever we had last time. There's just more of that in my office.
You always have food.
Always food. Gotta have food.
That's how you bring people there.
It is. It is for those chips.
Absolutely.
The chips are good. I'd come for the chips alone.
Dude, Capri Sun.
Um,
Whew.
Oh, Capri
What did you just
Sun.
say?
God.
the only reason my residents talk to me
No,
is
no, no.
because I have food.
Olivia, what did you
I did not have Capri Sun.
I am not.
Oh my gosh.
Capri Sun's gross.
Okay,
Love
no,
Capri
you
Sun.
first of all,
I love
that was
Capri
blasphemous.
Sun.
Never tried a Capri Sun. Oh, Lavina. Oh, Lavina.
You probably should. Now, don't fall to peer pressure. But
No,
it
I
might
am
make
peer pressure.
you
No,
do
you-
a Capri Sun.
You ever had have we had hot pocket yet with you?
Yesterday.
Yeah, really?
Yes. I was eating it and I was reading like the label and I was like, this is a hot pocket. I have to sleep.
Oh, I'm so proud. Which one did you eat?
Now I'm craving a hot
The
pocket.
pizza ones? Yeah. That's acceptable. That's acceptable.
These are making me hungry.
Ham and cheese.
I
ones
know,
are
right?
inside. I'm
Come
so
on.
sorry. We got on the topic of it. Well, here. Wait.
Are we getting differentiable on the line y equals 2x?
Yes.
Oh, we're just
Cool.
having to switch. Yeah.
Awesome. Awesome. And then like the second question you read on was satisfied with this 1 and -1. So those are equal and opposite sign, equal magnitude, opposite sign. And then, yeah, let's take a look at this. So I mean, so it's differentiable on y equals 2x. Just this lovely little steep line where everything looks like this. All the numbers on this line are x plus 2xi. And notice that that is just a constant multiple of this number, 1 plus 2i. So you're just taking scalar multiples, literally real multiples of 1 plus 2i, like it's a direction vector, like it's a basis vector, or something like that, to speak the language of linear algebra. Is this analytic? No, it's just like on a little line, right? It's got to be thick. There's nowhere. Analytic means you can move away and even just a little bit and be differentiable no matter what direction you move. So not analytic anywhere. What is the derivative on this? So only here can we talk about the derivative. Here, the derivative, did you get it, Noah?
Yeah,
What'd you get?
negative, or 4x minus I, or -1 plus 2yi.
Wait, so you got 4x minus I? Is that what you said?
No, 4x plus I,
Plus I, like this?
yeah,
Okay.
I think, yeah, cause it's just,
So you're using this formula up here?
yeah,
Okay, cool. So Noah's using this top formula, and then you also clearly used the second one. I could hear that coming.
I was,
So- Yeah. So let's talk about this because it's actually interesting. These aren't going to look the same if we just look at them naively without taking into account where differentiability occurs. So for this one, ux is 4x, vx is -1. So this actually should be minus. This should be minus I here actually, Noah, I believe.
yeah, not bad.
Does that sound right?
Yeah,
Because vx is -1.
I was being dumb.
Well, hardly.
It was an honest mistake, Noah.
Yeah.
It doesn't-
I had -1 on my paper, and then I said it and felt unconfident. And I was like, oh, ux and uy, because there was, I was thinking you go by both u's instead of both.
Gotcha.
Yeah, so
Oh, okay, gotcha.
doesn't matter.
Oh, good. So here's one expression for the derivative, which is pretty counterintuitive. But let's look at the other one, or f prime of z equals, so let's do the vy. V with respect to y is 2y. So this is the vy. And then I have minus I times uy, which is 1. So either one of these expressions, so it's just 2y minus I. Those don't look like the same derivative. This is some weird shit. What's going on? What happening?
Because we said 4x is equal to 2y.
Because the only place this derivative exists is on the line y equals 2x. And when I replace that y with 2x, I get that expression, and vice versa. Either one of those derivatives is totally kosher. Kosher. Is that helpful? No, does that help? I don't know if that helps resolve some of the things you were like asking about.
Yeah. Yeah, I forgot we could use it.
It's kind of cool. I like it. Really strange. Anytime there's something strange happening, right? It's anytime something we're used to isn't true anymore. It's awesome. Want to try another one?
Yep.
This one will be more basic. This is like, how's your Calc 1? I know, I knew that would strike fear. Luckily, it's all nice and private there with just you and the calculus. Find f prime.
The one thing in calculus that I have like a lot of confidence in, no matter how far away from Calc 1
Hell
I
yeah.
get from.
Find f prime. I'll put a couple up there.
Integration though?
Oh, well,
Different story.
wait till you see what integration's like for us, because it's nothing like it used to be.
But derivatives are the
What
same?
are that?
But derivatives are the same.
Why?
That's not fun.
That doesn't make sense to me.
In our integrals are almost always going to be like you'll see 0. If you don't know what an integral is in the complex plane, guess 0. That's a good guess. Or how about pi or pi I? Those are all great guesses. They're all like you'll get the joke when we get there for sure.
That's terrifying.
But 0 is always a good answer for a complex integral. And mostly no, because we will be working on contours, so we won't ever be doing like just raw antiderivatives
Yeah.
for the most part.
What does an antiderivative even mean?
I mean, just, it just means like, well, so when we do this derivative, we'll get f prime is this. It still means the same thing. It still means this is the antiderivative of whatever this formula would be. So they still have the same meaning.
Yeah, but in calculus that can mean assigned area.
When we speak antiderivative,
Yeah, like that's how I think of antiderivative in 2D. 3D. Not really sure.
I mean, when we define the antiderivative in terms of a definite integral, like, like f of x, let me just go to the real plane, equals integral from some start to x of little f of t dt. So like in this case, that capital F is an antiderivative of little f here. Is this, I don't know if that's what you're thinking. That's like totally legit.
Okay.
So here, f prime.
Is it any path? Or just specific? We can cover this when we get to
Yeah, why don't we, yeah, we might be heading out into the weeds a little too far.
The weeds.
The weeds. Let me put a couple others up here. So, our f of z, 1/2 iz. And then I've got a fun one here. Find this limit. Think L'Hopital's rule.
Jeez, I haven't got a minute.
Yeah, I know. Convince yourself that L'Hopital's rule should apply first, though.
Could U's and V's have I's in them?
No, U's and V's will always be. Why are we going there? Whoa. No, there's no kosher Riemann here.
Oh.
This is just like, okay, I was getting scared. I'm glad you asked. Answer to your question is no, and the second thing is stop doing that right now. Because it's not good for your mind right now.
That was funny.
Just use calc. Just treat z like x.
Okay.
Just like take a derivative. Put it back in calc 1. Poof.
Dude, when he realized what you were doing, his heart sunk into his stomach, I swear to God.
No.
It's visible distress.
It's like my sister. Yeah, it's the same feeling. My sister was like bitching about my mom to me, and like a dumbass included her on the text. And then my mom chimed in, and my heart sunk, and I wasn't even the one who did the dumb thing.
Like, how do you, imagine being caught in that awkward situation, like, oh, mom's here.
And it could have been so much worse too. What she was like, thank God you only said that.
Oh, jeez.
Yeah. My mom's a real trouble.
I bet your mom watched our videos.
No, she wouldn't make it through the first 5 minutes of this
It
class.
happens to most of us.
I should not eat this Jolly Rancher
Yeah, you
right
should
now.
do it.
No, because then I'll like have it in my mouth and I'll be like,
God, he has self-control. That was one of us. And only one of us.
well, when I'm here on the job, you know, trying to look super professional.
Gotta be civil.
Gotta
you
be
know.
civil. Gotta
Yeah.
keep my shit together.
Sure.
And like these things give, you know, it's kind of like, what do I remember? And if I don't remember it, this becomes insurmountable. What did I use there?
Don't forget.
The freaking what? Yeah. Chain rule. That's why we're reviewing this today. Chain rule.
Never asked you what the name was.
I knew what it was. I just
Yeah,
didn't-
exactly.
Derivative of the outside, right?
Yeah.
Times derivative of the inside. And that 2i is just like a number, just like there might as well be a 7 there, and I just copy it over. Oh, this should be 4. Maybe that's why I saw Lou's face. Maybe it's something. That's better. Is that better, Lou?
Yeah.
Yeah, I was like, then you started talking, I was like, I'm not gonna cut you off over like,
Thanks.
that's small.
I appreciate that. But yeah, it's okay. I watch for the subtle facial expressions to like help me stay decent.
Wait, yeah. There's a rule for that one.
That's a 2, right?
Yes.
2IZ, yeah.
Yes. Yes. Good question.
You really have to pay attention to the, if he puts the slash.
The bar.
Yeah.
Yeah.
The x of b over b squared.
Just the loading.
Pretty low.
Yeah.
Or you just make life easy. I mean, you can quotient rule that thing, which is awesome. I'm glad you're thinking of that. But it's also just this and a power rule. Either way you do it, you'll get the same answer. That quotient rule is going to look not great.
Oh,
No, that's great.
Does it?
Oh, I can simplify this more.
Yeah, there'll be some simplification that'll need to happen.
Yeah, it's easy.
Yeah, okay.
Oh, you just took the Z out?
Yeah.
I mean, I just rewrote the z as z to the negative first.
Because then it becomes a coefficient.
Yeah,
Yeah.
yeah. Then I just had fun, because I don't like having eyes, and I don't want for you to have eyes in the denominators either. Just a little tip about my complex aesthetics. I like having those eyes on top.
Oh, wow, I did.
You are a genius, Levita. You are. Don't ever tell yourself
I
otherwise.
was overthinking the first one.
No, it happens. Don't even worry about it. It happens. I think we're like legally obligated as math people to overthink.
no, literally during stats today, she was just asking for how many numbers and
Uh-huh.
everything. I was like, this is way too easy.
Like, there's no way she's asking me for
No.
an answer from 1 through 5.
No.
and I am doing weird stuff here intentionally, so we'll talk about it.
It's 14. Yeah. Whoopsies. Did I skip? Oh no.
Did what?
That's the, yeah, because what you did over there is what you're doing for the third.
Yeah, I'm just doing, here I was seeing if we had a 0 over 0 form so that we could apply L'Hopital's rule. And we do. And then here I just took the derivatives. And now I'm gonna plug and check again. And everything's gonna be okay. And the stuff I'm doing with the powers of I is how I think, we haven't really talked about it, and I just thought we'd take this time to do it. How I think about simplifying powers of I that are, above 4, because otherwise we can kind of think of that easily. And we will, of course, talk about all this. You just don't guess things like that. It's been hungry, jeez. So is there anything up there that is striking you as I would definitely want to talk about that, go through that? I got a few comments to make, but
Why do we know that we can just do the same thing for, I took the answer to this problem, which I probably shouldn't do.
did you just answer your own question?
No,
Oh,
but why do we know that we can just treat Z the same sex? Is that long and involved proof that I don't want to know about?
I mean, let's think about it. So let's actually, that's a great question. Let's talk about it. So let's say I asked you to find the derivative of Z to the n. Great question. So I'd go, let's say I don't know anything, and I've just got to go to this freaking definition. So I go, all right, here we go. I'm just going to the definition of derivative. So Noah, I want you to just think about, does it matter if I have a Z or an X in here? In terms of how this algebra is going to play out. Like in simplifying this expression over here, does it matter if that's a Z or an X? Because for all we know, this could just be Calc 1 where we use Z's instead of X's, right? That's literally just the definition. Like if I said, hey Noah, what's this? You would say,
Yeah.
and then you would simplify. And let's think about it. You probably have, it's been a while since you thought about this. You first have to get this expanded out, which is a binomial expansion. And so let me just kind of start on that. So this, if I multiply this out, is going to be n choose 0, x to the n, h to the 0, plus n choose 1, x to the n minus 1. Now I start kicking in powers of h. And that, so that my net sum power, my net power is always going to be n. Is it okay if I erase this one? Is this one cool?
Yeah.
Okay. And then plus n choose 2 Is this note, when I say the choose, is that cool?
Learned about that today.
Awesome. Awesome. Outstanding. This is combinatorial, combinations, x to the n minus 2, h squared plus blah, blah, blah. Eventually I get down to 0, x to the 0, or I've got n choose n, x to the 0 power, so I'm not even going to write that, h to the n. And everything before that had an x in it all the way up to the n. And then minus x to the n all over h. So, notice that this and this cancel. And so what I'm left with then is a bunch of terms, each one has an h in it.
And then you divide by h.
And I cancel out an h. So
And nothing changes if we just do z.
exactly.
Okay.
So the ways you actually crank out these formulas are identical. It's just z instead of x. So let me just finish this up so everybody can see. So this first one is going to be, like, cancel all the h's out, and you're going to have lim. I should have had the lim out in front there. Cancel out an h. So I've got n choose 1, x to the n minus 1 plus, and then each one of these is just going to lose an h out of it until I get to the very end. Let's not be super pedantic about it. I got h to the n minus 1. And then I've already divided out the h. And so now I just evaluate the limit. And that just means everything with an h goes to 0. And I'm left with n choose 1, x to the n minus 1. What's n choose 1? Well, let's write it out. That's 1 factorial, n minus 1 factorial, x to the n minus 1. What is that? N. And that's called the power rule.
So the power rule works.
Yep.
And if we were just to do the same thing with most other things, we find they work.
Absolutely.
Okay.
Everything looks the same. It's just that when we get down to that like idea of differential, when we start going to u plus v form, things get weird.
Yeah.
But otherwise, like, your functions are your functions. I mean, it's going to turn out, we haven't talked about e to the z yet, but it's going to turn out that this is just e to the z. Beautiful, just like we're used to. It's going to turn out that the derivative of the principal branch of natural log, which we haven't got to, notice I have a capital L there, is 1 over z. You know, all that good stuff is still there. All your formulas, right, intact. No, when we get to this, it'll be weird, but the derivative of sine of z is what? Tell me. Cosine of z. So all that shit. Your table from Calc 1 is going to serve you well in this class.
Same with antiderivatives?
Yeah.
Okay, cool. Just checking.
Yeah, all
So-
good.
Antiderivative of cosine of c would be negative 7. No,
Yes.
negative 7.
Yeah.
No.
Yes.
So how's integration different then?
Oh boy.
That's going to take time, because in what we're going to end up doing, Lavina, invariably, there's no reason to do integration in the complex plane unless you're integrating around a contour. So we'll do like line integrals, like you did in Calc 3, but in complex plane.
Oh my goodness.
Yeah, because like complex integrals don't ever just show up on their own. They always show up as part of a contour, something, or contours involved. So there'll never be a case where I'm like saying to you, find the antiderivative of 1 over z. There'll be a contour involved.
Interesting.
And the number is going to probably be 0 or 2 pi I or something like that. But that's like, that'll take more than me just saying it.
Okay.
Yeah? This is a bit, you'll get this, like, it's not completely true, but it's like close enough to true that it's a funny joke for only me right now.
Okay, I have one question.
Cool.
So we have over 14i. How did we end up with 7 over 49?
How do you divide by a complex number? What do you do to divide by a complex number? What do I multiply?
Oh.
Multiply by the conjugate.
Definitely, that's negative 7 over 49.
Did you not hear me ranting about how I don't like eyes in the bottom?
Jeez, Lavina.
That was literally like 2 minutes ago.
Jeez.
I'm short term memory.
He was so offended.
Yeah. Furious. You've seen me lose my temper a lot, so. I don't think I've ever actually been angry,
No.
like,
Ever.
not in our classes, no.
Sometimes what you do is just the disappointment, but not like wow, I'm so disappointed, you guys. It's like
It gives
I'm
you a
thinking
look.
we could have looked at homework before now, or like
Yeah.
I'm thinking we could have done better, you know, stuff
Yeah.
like that.
It's like the dad is.
Yeah,
Oh, good.
yeah. Disappointment,
The
no.
worst kind.
No, mom disappointed.
No, that's the worst.
Whoa!
Especially when your mom's crazy.
Kim just looks at me a certain way, and I'm like, I'm gonna leave.
So how do we feel about everything that happened in these little warm-up problems? Feeling better?
Yeah.
I believe so.
I want to kind of introduce, we're going to start looking at functions. Like, we're going to actually start talking about these functions, but we've got a more basic class of functions to look at first. That's really cool. It's going to open up a new way for us to look at the complex plane that I've hinted at. And it's actually going to provide you with a great deal of insight. It's going to be awesome. So let's just start talking about some special functions. They're special. So the first one I want to talk about is this class of functions. You take a complex, so it takes a complex number z, you multiply by a, which could be a complex number, add a complex number, divide by another linear combination like that, so cz plus d, and here a, b, c, and d are potentially imaginary. So this class of functions is called linear fractional. And I think that name, when you look at this, you're like, oh, it's a fraction of linear things. Cool. All right, that's not very creative. But here's the better name for it, a Mobius
Yeah.
transformation.
Yeah.
Yeah.
Are those 2 dots above that?
That is an umlaut, yes. Mobius, as in the one-sided strip Mobius. So these are pretty interesting. What are some things that we can say about this right off the bat? What is its domain?
Everywhere CZ is equal to negative D. Everywhere
Give that man $1.
everywhere Z is not equal to negative D
Give
over
that
C.
man $1.
That's right. Where we don't divide by 0.
Practice.
I might have hinted at that a little early. So, domain where, let's just say what I like what Noah said, because where that is true, i.e. where Z is not what? Negative D over C. Indeed. Provided C isn't 0. If C is 0, what is our domain? Provided D is not 0. So C is 0, D is not 0, what's our domain? The whole complex plane?
All of it.
All of it, because it's just this. And you can do that anywhere. You don't have to worry about dividing by 0, so, or anything funky happening. Cool, good stuff. What is the image of 0 under this transformation? Temperature's starting out chill. It's like now we're in the bathtub and I can start turning the water temperature up. That's good. All right, so what is this? If we just think in terms of, just think about it naively like you would if that were just x's. It's still the same stuff. What was it?
She said B over D.
B over D, incorrect. We got that for 0. So that would be cool.
Will be A over C.
A over C. Think about when Z is.
Oh,
Yeah, right.
I was,
So we've got an infinity over infinity. What rule could I
yeah,
use?
no, that's what I was doing, but I kind of was blew off. Like,
You got a little off, yeah. So you can see this with the L'Hopital's rule, or divide. You could rewrite this like this, right? And this is a real classic algebraic way to see it. And then these pieces die off as the magnitude of Z grows, and so you've got A over C. I'm getting a really weird old memory of a fake cherry flavor. This is so weird. I don't know what's in this. I better stop huffing these things.
Jeez, Dr. T.
Jeez.
Oh, I'm pretty sure for infinity ones are infinity you do bubble button.
You what?
exactly.
What's
Do
going
you
on?
guys not know that?
No, what?
When it's like when you're taking a limit of something to infinity, it's just bubble button eats DC.
Exactly.
Bobo is
Yeah.
wait, now I'm like, okay, hold on. Bobo
No
is
pressure. Everyone's staring at you.
Bobo is like bigger on bottom 0. Then button is bigger on top is like non-existent, which is infinity or negative infinity.
Yeah.
And then east DC is like
Equal.
some sort of equal coefficient something, then you divide the coefficients.
Yeah. Yeah, that's good. That's good. I've never heard that little mnemonic.
Really? I
Yeah.
learned it in like Calc 1.
Wow.
Dr. T taught me Calc 1, so.
And I never heard it. So
No.
I've never said that before.
No.
But Grace is just saying they're the same degree. So the ratio of the leading coefficients is your infinite behavior. Bobo, beep, bop.
Bobo button eats DC.
Bobo button, east,
Eats like eating.
eat,
Oh, no.
I
DC.
forgot what the EAT is. I think it's like equal something.
Huh.
And then
That's-
DC is just divided.
That's wild.
I was like, I was speaking the same language.
I was baffled for a second, not gonna lie. She had me.
Let's pretend infinity is a number.
Well, okay. Wait, is this, so does what we're writing now go with?
Yeah.
Okay, still, cool.
By the way, if anyone wants to know what you're gonna be doing a lot of in modern geometry, it's this.
It's super fun because I don't have to take that, so that's fun.
Well, it gets you fun shapes, is what I will say.
Are you thinking about like projective geometry or something else, or spherical geometry? Or? I've never taught the class, so I
You
don't
start
even know.
with Mobius functions before you go.
Oh, do you?
Before
Oh.
you specialize the Mobius functions to give you hyperbolic and the other one.
Oh, spherical.
Yeah, spherical.
Oh, cool. Now I know what I'm going to be teaching.
Because,
Thanks.
yeah, all transformations
Did you just-
are.
Yeah, I don't know what that class is about. I don't know what that class is about.
Well,
When
that's
you-
the way Cyber taught it.
When do you,
Oh, I'm not worried. I'm excited.
Yeah.
Yeah.
oh, and you're teaching it next semester?
Yeah. As long as I'm like a day ahead of the class, I'm fine. It's like, yeah.
So we have Pat Knott, who
She's
wrote
more
her
than a day ahead.
quizzes in July.
Yeah, she did
Literally
everything.
wrote everything in July. And
True.
Dr. T said, I don't know, as long as it's a day ahead, it's all right.
I do. I fly by the seat of my pants.
So just proof that you don't have to be, like, look at where both of them are.
Exactly.
There's
Total
lots of different
opposites.
ways in this life. There's
Total
many
opposites.
routes. Yeah.
Absolutely. Infinitely many routes, Dr. T.
And I could definitely not pass one of Dr. Patnott's classes. This is just like the structure. I do not function in structure.
No, we
I
know.
crumble.
I am well aware of this.
Dust.
Crumb.
I can't even do rubrics. We're like, looking at rubrics to hire people, and like her and Cybert are all like, well, what if we tweaked it so that 2 means this? And I'm like, I'm fucking not even gonna use this thing. I don't even know how to, this means nothing to me.
He was just there for the meeting and called me.
No, I have to be at the
Yeah.
meeting, and it's just like, I know how to fake it. That's for
Absolutely.
damn sure.
It's how you make it, that's the
As you should.
That's right, exactly. But like rubrics, like Dr. Padnott lives by a rubric, right?
Yeah.
Like literally, not even like, not a slam or anything. She's just an incredibly structured, the most structured human being I've ever met in my life.
I would agree with that
Yeah.
statement.
Yeah.
I would agree with that.
And I am one of the least.
I would also agree with that statement. You are spitting nothing but facts right now.
Alright, just
Dr.
spitting
G.
facts. Alright, so let's pretend infinity is a
Sorry.
number. Let's pretend infinity is a number. And I think we might even have a bunch of properties in our book. Let's see, wait, who has my book? Somebody has my book?
Noah has
Noah has
your
my book
I
now.
still have a copy problem.
So this is like a thing that I tell everyone not to do, right? Like, if you were in my calc class, I'm like, infinity's not a number, it's an aspiration. It's a place, it's an aspirational thing. But now it's just like, now we're like, I'm gonna use infinity. We're gonna do stuff to it. Let me just get all
The
the
top of the sphere that is the real number, or that is the
Indeed.
complex plane.
Indeed. Way to spoil it. But
Modern geometry is what we did.
yeah, no, quit spoiling it. That's enough, Noah.
Okay.
Jeez, Noah.
Sorry.
Please, my God. I'll just go back into my math.
Unless you're coming to math.
So, yeah, this is a definition. We're gonna consider the extended complex plane.
Oh, okay. It goes further.
Extended, yeah, it goes one number further.
Okay. As it should.
So we're gonna, what do they use here? Star, that's classic. They use like a C, and they have a little hat on it, so circumflex. They take C, so this is equal to C union this new beast we call infinity.
Oh, that's what
Use
you
a
said.
number.
Yeah, so we tack on a number, and that number is just,
A whole other beast.
yes, the incomprehensible. Just stick this tiny incomprehensible number on there and you'll be good. So, we got some properties, so addition with infinity is commutative and does not alter infinity. So that's true for any A in the complex number. So let's see, for all A in C extended. So even infinity plus infinity is infinity.
As long as you know what he meant, everything's fine.
B, if A is not 0, then infinity times A is equal to A times infinity, and that's just infinity. Can't go wrong. What's 17 times infinity? Infinity.
Beautiful.
Isn't that nice?
Why are we on?
What's 0 times infinity?
0?
Nope.
Incomprehensible.
It's incomprehensible. This is an indeterminate form. You would probably rewrite this in a L'Hopitalable kind of thing, and then this would be infinity down at the bottom. And then we have, and this is kind of just a special case. This is really just saying what we've already said. It's included in that. Infinity times infinity is infinity. A number divided by infinity. Oh, this is actually for A and just C. Sorry, take that out.
Wait, where?
Just take the circumflex off the A. Yeah, that's why they have this as a special case, because these properties hold for finite numbers. So if A is finite, this is all good. This was what was bothering me, is that a finite thing divided by infinity is a 0. And then we got one more. This is property E. If A is not 0, then A divided by 0 is infinity. So these are kind of like, right, you just swap the place with the infinity and the 0.
No, we are not divided. We are not divided by 0.
So, think that's indeterminate because those infinities can be, in theory, not the same infinity.
Yeah, because the rate at which we're approaching that infinity can be different. Yeah, exactly. But we're not getting into like hierarchies of infinities like we could, but we're not like going, that infinity's like LF0 and then, you know,
There's
on the,
hierarchies.
what's that?
There's hierarchies.
If you do real analysis, you'll understand.
Yeah.
There's infinitely many, there's a chain of infinities and they're each bigger than the previous one.
Yeah, that's exactly what we said when we looked at too.
It's awesome.
Yeah. I'm just really not okay with the whole dividing by zero
Yeah,
equal
no.
infinity. That's just,
But this is literally what like Calc 1 students do all the time.
Yeah.
They're like, top is fixed, bottom's going to 0, infinity. And honestly, this is nice because in Calc 1 you'd have to worry, am I approaching 0 from this side or this side? Is that plus or minus? We don't have a plus and minus infinity. We have one infinity, not a minus. We just have one in the complex plane. And let me explain why. Noah was hinting at it. So what makes this make sense is a different vision of the complex numbers. Let's see, do we have a picture of this in our book? Probably not. There's not a lot of pictures in here because they cost like 5 cents to add or something. So they were trying to
Were we
keep this
not worth-
cheap. No, well, I mean, it was free.
I got
So, yeah, you know. So how does this even make sense and how is it going to relate to that? And that's probably what we'll just start these last few minutes. The Riemann sphere.
man, that Riemann guy gets around.
Oh, Riemann was insane. Riemann was like, yeah, he
Oh, man.
was the shit in the early 20th century. So the Riemann sphere is a way to envision and encapsulate the extended complex plane. This only works with the it kind of can work with the not extended, so you just have to not think about infinity as a whole. But basically the idea is this: instead of a plane, we have a sphere. We have a sphere, and at the bottom of the sphere is 0. At the top of the sphere is infinity.
Okay.
And every other complex number between 0 and infinity is on this sphere. These are the ones of larger magnitude, these are the ones of smaller magnitude. Where this equator falls depends on how we set up the Riemann sphere, and there's actually many ways to do it. At least there's 2 good ways. And let me show you the first one. So like, how do we make sense of that? How do we put complex numbers on there? It's kind of cool. So what we're gonna do is, first off, let's imagine we have the complex plane. And this is great because I get to draw 3D and that always makes me super happy. Here's C, complex plane. And then, like, let's see here. Oh, we'll make that the real axis. And then we'll make that the imaginary. So I'm putting I times R. If you've had like abstract algebra, you might call that like, you call that like an ideal or something. Something like that. Yeah. I don't care either. Yeah, we definitely didn't do it in
Sure did.
our class. No.
No.
So imagine a sphere that's setting on the plane right at the bottom. And I'm going to do this in a different color so it helps. And then I'm going to bring in like good visualizations and not my garbage. But here we've got a sphere that sits atop it. Sits atop the plane, just tangent at the base. And the height of the sphere, the radius of the sphere is 1 unit. So it's a sphere of radius 1. Let me just write that. Sphere of radius 1. Tangent to 0 in the complex plane. And then, so like, how do I take a complex number here and map it to the sphere. And here, it's a really cool scheme. I need another color. Handful of color. So what I'm gonna do, let's say I take this Z here and I wanna figure out where it is on the plane. So I go to the North Pole.
Absolutely.
I always go to the North Pole. That's what we're gonna call infinity. And I draw a line between the North Pole and that number. That line will intersect this sphere somewhere
Okay.
on the surface.
Okay.
That number is the representation of that number. So where the line from infinity to Z hits the sphere is the representation of that number. And vice versa, you can work this backwards. What does that represent? That. So let's think about this really quick. What does it look like? What is 0? Where does 0, what does the line for 0 look like? Straight down, right? So like 0 is this line just running straight down through the plane. Notice that as this line moves away from the sphere, think about this sphere. You got this like round surface and you're tacked up here. The further you get away from it, the more tangential this becomes. Does that make sense? That the further out the Z is, the closer this line will be to tangent. When you're tangent, you're like out at infinity. So we're kind of like, and I'll just say this and end it, it's kind of like we've taken the complex plane, we've grabbed the edges of it, we've cinched it up. So here's the cinching process here. I think I drew this picture once before. Like that. And then just keep cinching it together. So you're grabbing infinity and pulling it to a little point and bundling up the whole plane.
You're grabbing infinity.
You are grabbing
Literally
infinity.
been told all
Take
my life
infinity.
that infinity was not a number.
Grab it by
and
the
not
roots.
candy.
Yes, ma'am.
Can the line ever cut the sphere to the
And we can prove that. We can actually literally work out the equation for a particular x plus iy to what the coordinates are of the sphere. It's unique. It's 1-to-1 and onto.
Yeah.
Woohoo!
I just broke my brain a little bit.
Yay! I think your brains haven't
Modern
broken in a
geometry
while.
is fun. It doesn't break your brain a little bit.
See, geometry wasn't my favorite thing that in the math world.
But like,
This
imagine
isn't the
doing
same.
this geometry on a sphere with a complex radius. What does that even mean? Who knows?
Remember in real analysis we were doing something where we were like in a line doing something and then something happened and then that point became infinity, and so we're bringing infinity to that point.
Might have been one of the classes that I wasn't there for.
There was way too much detail in that story. Remember when we were in class and something happened?
Remember that one day that we were talking about that one thing for like